Kia ora tātou. In this video we're going to be looking at strong versus weak acids, or the difference between strong and weak acids. So let's think of some examples of some strong acids. So all of the acids that we would have come across in year 11 were strong acids. All of the acids in the, well, most of the acids in the chemical cupboard in the science room. So some of those examples would be hydrochloric acid. This is classic. One of my videos where I start with the eraser. We could have nitric acid, which you know 3, or we could have sulfuric acid. Those are all examples of strong acids, and they're all strong acids that we came across last year. Now this year we're going to be looking at weak acids as well. So what are some examples of weak acids? Well, basically anything that you find in the pantry that is an acid would be a weak acid. You wouldn't find strong acids in the pantry. So examples of acids in the pantry would be vinegar, or it's also called ethanoic acid. Maybe you'd have citric acid, and possibly tartaric acid. So for the level 2 chemical reactivity, citric acid and tartaric acid their chemical formula are too difficult, so I haven't seen any questions that come across any acids like that. So basically it's always going to be either vinegar or any carboxylic acid if we have a weak acid. So we can just about get rid of this and just really be looking at carboxylic acids when we're talking about weak acids. Unless, hopefully I don't get proven wrong. So let's look at what the difference actually is. So we'll take hydrochloric acid, and we'll look at how that reacts with water, or hydrogen chloride, how that reacts with water, and then we will look at how ethanoic acid or any carboxylic acid reacts with water. So let's draw this out. So if we've got HCl, and I'm going to do the H with a red pen, HCl, and when this is just by itself, before we put HCl in water, it's called hydrogen chloride, and it's actually a gas. And then we can mix that with water, which would be a liquid, H2O liquid. And so the definition of an acid is that it is a proton donor. So because this hydrochloric acid is an acid, it is going to donate its proton, or its hydrogen ion, to the water molecule. And what we're going to get is that because this hydrogen ion has been donated, we get what is called H3O+, and that is a hydronium ion. Hydronium ion. And then we're just left with this little chloride ion that just hangs out. And that would be aqueous. And I've lied here. Why have I said that's a gas? That would be aqueous as well. So yeah, hydrogen chloride, and then water, and then the chloride ion. So once this is reacted with water, we get a solution of hydrochloric acid, and that's what this would be. So just to explain a little bit about this hydronium ion, so this will be new to you this year. Last year we would have looked at HCl dissociating in water, and we would have just we wouldn't have shown it actually reacting with water, and we would have ended up with it looking like H plus Cl minus. So, and then we might have put in the states as well. And so what this would mean is that there would just be some protons floating around in the water. That is fine to show as a simplification of what's actually going on, but in reality there wouldn't be protons or hydrogen ions just floating around in the water. They would react with a water molecule and form a hydronium ion. So we will still use this sometimes, the H plus, as a simplification of the hydronium ion, but whenever you see H plus, just know that what it's actually saying is that there is a hydronium ion in that solution. So there was a bit of a tangent, but that's just some important information to know. This is a strong acid because every single one of these hydrogen chloride particles would react with the water particle there. So if we started off with 100 hydrochloric acid particles, and there were enough water molecules, so well more than 100, then every single one of these would become a hydronium ion and a chloride ion. So we'd end up with 100 hydronium ions and 100 chloride ions, and we would end up with 0 hydrogen chloride particles on the left hand side. So that is what a strong acid is. It means that every single acid particle will donate a proton when it reacts with water. The difference between that and a weak acid is that when we're talking about a weak acid, not every acid particle will donate a hydrogen ion to water. So let's have a look at what ethanoic acid would look like when that reacts with water. So CH3COO, and then I'll use a red pen again just to show this hydrogen ion getting donated. That will, by itself, when there's no water around, that's just a liquid, and then we've got water as a liquid. So the same thing as before, this hydrogen ion will be donated to the water, and what we get is H3O+. So we've got our hydronium ion again, and then we get CH3COO-, and that is aqueous. Just run out of room. So we've got ethanoic acid plus water goes into hydronium ion and ethanoate. So I'll just write that there because that's a tricky one, ethanoate. The thing is that if we had 100 of these particles and there were enough water molecules, not every one of them would react with the water, and then we would get some of these particles then reacting in the backwards direction to form the reactants again. So what might happen is that maybe one of these particles for every 100 would react. So once we've introduced these 100 particles to water, we might only end up with 99 ethanoic acid particles and only 1 hydronium ion and ethanoate ion. So that means that in the result, the solution will not be really strongly acidic, because there will be a low concentration of hydronium ions. So if we've got an acidic solution, it's the hydronium ions that actually are the things that then react with anything that we add to the solution. So if we had a slightly acidic solution, we added some magnesium metal, it would be the hydronium ions that react with the magnesium metal to bubble and form that hydrogen gas. So that is a weak acid. It will only slightly dissociate. So that will mean that we've got, for this, we looked with our equilibrium reactions. When we see that sign, we know that there's going to be an equilibrium constant. So this would be very, very low, meaning that the reaction barely proceeds. It does a little bit, but not very much. And the other thing that I'll just add in, that we'll get into at a later video as well, is that instead of this being called the equilibrium constant, we call it the acid dissociation constant. And so instead of Kc, that is called Ka. So thanks for watching this video. There's quite a lot of information to take in on this, so you might need to watch it once or twice and maybe take some notes on it. Yeah, cheers for watching. See you for the next one.